Let's talk about another way to produce ROC curves. So ROC curves can be produced in two ways. The one that I just showed you, which is for a single real-valued classifier. In that case, the ROC curve evaluates the classifier. But there's another way to create an ROC curve where you can use an algorithm, single algorithm, and sweep the imbalance parameter across the full range and trace out an ROC curve to evaluate the algorithm. So one is a property of a classifier, single classifier, and the other is a property of a whole algorithm. So let's go over this way again, and I'll repeat how to do that. So let's say that we have our classifier, our function f, and it's increasing along this direction. And we could place the decision boundary anywhere we wanted along here. So let's start from the top and sweep this thing down from top to bottom, and every time you move it, you record the true positive rate and the false positive rate. And then you plot all those TPRs and FPRs on a scatter plot, and that's the ROC curve. So let's do it. So we swing that whole thing down that way and record the true positive rate and false positive rate as we do it. Okay, so and that traces out this whole curve. So that's the first way to create ROC curves. And that's for a single classification model. And now let's talk about how to evaluate an algorithm. You remember the C parameter from the imbalanced learning section? That's the one that allows you to weight the positives differently than the negatives. So here, I'm going to sweep through values of the C parameter and fit a machine learning model each time we adjust this C. And we're going to start with C being tiny. So the classifier doesn't care about the positives at all. It just cares about getting the negatives right. And guess what? It got all of them right because it just classified everything as negative. Then we adjust C, and we get this one. And then we adjust C again and get that decision boundary, and this one, and that one. And as you do this sweep, you get different models each time. But you also get a true positive rate and a false positive rate each time. So you can plot those values on an ROC curve. But this ROC curve evaluates the whole algorithm and not one classifier. Now, what's the advantage of using one of these methods over the other? Right? It's not really like that. You can't really say that. Right? One of these two things is an evaluation measure for a single function, and the other is a measure of quality for a whole algorithm. Usually an algorithm that's optimized for a specific decision point can actually do better than an algorithm that's optimized for something else. Okay, so usually you would expect to see the ROC curve for the whole algorithm, which is optimized sort of at each point on this curve. You'd expect that to do better than just a single classifier. So every once in a while you do get a surprise and something weird happens, but in any case, this is the idea. If you use the algorithm and fiddle with the class weight parameter, you're essentially optimizing for each point along that curve. Whereas if you use a fixed classifier, you might be optimizing for one point on that curve or for something else entirely. So you wouldn't expect the ROC curve to be as good. Okay, so here ends the discussion of ways to produce ROC curves.